He's been doing a lot of different things. Let's put it that way. He found his magic bullet and he's applying it in different scenarios like dark matter detection using DAMIC in the DAMIC experiment. Connie looking for coherent neutrino scattering at nuclear reactor. And the recent result from CENNS, the new detector, skipper CCD detector, which is really exciting. Thank you for coming.
Okay. Yeah, so I'm going to tell you mostly about Connie, the work we are doing for coherent Neutrino-Nucleus interaction at the nuclear reactor in Brazil. But this is the technology that we use also for other experiments. I mentioned a little bit about that, and I will, Rupa asked me to show what the recent results that we have for CENNS, and I'll show that is actually a result from a very short run on the surface, but we'll get to that in a second. Okay, so this is an effort for looking at Neutrino-Nucleus elastic scattering, coherent elastic scattering, and the idea here is that if you have a low energy neutrino, low enough energy, then when it interacts with a nucleus, it doesn't see the inside of the nucleus and see the whole thing as one coherent entity. And the cross section for this interaction will be the same case, essentially because the nucleus is here, right? So like this. So this gives at low energies a high cross section for this type of interaction, and you have to have a neutrino energy below 50 MeV for this to be valid. Reactors are ideal for this, and there are other possibilities to look for this coherent scattering, and one that was successful, I mentioned that in a second. Okay, so this has a long history. In 1974, people were already starting to discuss the coherent effects in neutrinos, and maybe 10 years later, more detailed experimental or prediction of experiments that would start seeing this. And the point that was made at that moment, before, is that these detectors will need, the cross section is large, but the detectors need to be very low threshold. Right? So there has been a lot of effort on trying to get to this point, and the results are really exciting now, as I will. So why do we bother? I'll split this in three categories. First, this is very important for future dark matter searches, and this is how I got into this business. Because this, as I'll show you with one plot in a second, this coherent scattering of the neutrinos is the limiting background in the next generation of dark matter detectors. So, in a few years, the dark matter detectors will start being limited by this process. So it's good to understand it. And then there is a window for new physics, because you're looking at very low energy neutrinos. You can look for the anomalous magnetic moment of the neutrino. You can also imagine some non-standard interactions like a dark photon that will have impact there. And then, finally, if you really have a new way of detecting neutrinos, then you can, very low energy neutrinos, then you have a new way of performing neutrino oscillation experiments with, given the energy is so small, the scale, the baseline for these experiments is going to be very small. So that's a part of new physics, and then there are technological applications that have been discussed. Right. So I'll go quickly over this before I get into what we are doing, just to motivate a little bit. So So these are the typical plots for the dark matter searches, and this is from 4 years old, right? A little bit less than 4 years old. There's a lot of activity everywhere, right? But this is cross-section, this is mass, and the point is that once you drop in the mass, you get to this yellow region where the background from neutrinos, atmospheric or solar neutrinos on the low energy, on the low mass, and atmospheric in this higher mass area, start being the dominant background, irreducible background in some sense. Now, we can talk about the ways to introduce it, but a very important flaw for this experiment. But until very recently, we had not detected this process anywhere. So it was very important to understand what it is, so that we could actually know what we were seeing when we get there and the dark matter experiments. So I am especially interested in this very low mass region of dark matter searches, and that means that I want to see very low energy recoils in my detector from the dark matter, and also very low energy recoils from the coherent scattering. So I need to look at the lowest energy part of the coherent scattering process, not at the 50 MeV, which was the highest that we could do. Okay. I will just flash this slide. This is a paper from Ronnie Harming, one of our colleagues at Fermilab, but it has a nice summary of different processes that can introduce excess number of events in dark matter searches for because of non-standard interaction with neutrinos, right? So this is spectrum of dark matter nuclear recoil searches. So this is energy, this is the number of events, this is the data that we had, again, a few years ago. And Ronnie and his colleagues calculate how anomalous magnetic moment of the neutrino for B minus L, boson minus electronic number, at the gauge B minus L particle number, like a dark photon, could introduce large variations in this rate, in this background rate. So new physics can affect very significantly that. So if you understand these low energy interactions of neutrino, then you can access a window to that new physics, right? I'll mention a little bit more. So this happens in the nuclear recoil, in the electron recoil, and the effects at low energies could be many orders of magnitude the standard model. This is electron recoil, and you can see that with anomalous magnetic moment of the neutrino can have electron recoils more than an order of magnitude larger than what you will get from the standard model. Okay, and there's other experiments looking at this. And the last part of the motivation is that if you build a compact detector to look at the antineutrinos in this way, using the coherent scattering, then you can monitor a nuclear reactor. Right? You can put this inside a nuclear reactor and measure the flux of the nuclear reactor. It turns out that there is a treaty between many countries to get rid of the plutonium that is used for weapons. And the way to get rid of that is to use it in something that is called a breeder reactor. And the breeder reactor has a special signature on low energy neutrinos that cannot be detected with the more standard inverse beta decay neutrino detector. So you really need to go to low energy. So people have approached us and said, well, let's try to build a very large, a massive detector, 20 grams. It's not very large for neutrino standard, but it's a 20 kilogram detector for monitoring reactors using the technology that you are proposing. Right? So there is interest from many places. It was very exciting last summer, in August. that this was first observed by the Coherent collaboration using neutrinos from the spallation neutron source. So stop pions producing neutrinos, I'll mention that in a second. But this was an observation, very nice observation with this neutrino, compact neutrino electron, cesium iodide, very big success of the Coherent collaboration last summer. So this is for neutrinos that are on the high side of that 50 MeV scale that I mentioned before, but it's a very, very impressive achievement. So what are the two ways of looking at this? So one way is to use neutrinos, and I have here in the bottom, neutrinos produced by stop pions decaying at rest. So you stop the pion decay, produce a neutrino, so you have a timing signal that you can use to look at these neutrinos. And this is the way that the neutrinos were detected in the Coherent neutrino scattering was detected by the Coherent collaboration. It has higher energy recoils, so it's easier to see because the recoils are higher energy. So it has pulse, because of the structure of the beam, you have control on the background because of the timing, and has to deal with some beam associated background. Right? So that's one way, and this is the way that they were detected. The other way is what we are trying in CONI, and what people here are trying in minor. So neutrinos, using neutrinos from a nuclear reactor, which has a very large flux, because you can get close to the core. So it has low energy recoils, so they are harder to see in the detector. You need a lower threshold detector. And you deal with the background by shielding, you don't have timing. But I am very interested on this part because it's a window to the very low energy neutrino sector. Right? It's significantly lower energy than this, and really, as I was mentioning before, all the effects of new physics really manifest dramatically when you go to low energy. So some of us are trying to do this upper part. So we have a collaboration with about 20 people, and our reactor is in Brazil, so we have a lot of South American collaborators. So now I'll tell you about the detector technology that we use for this CONI experiment, which is our effort for detecting the Coherent neutrino scattering in the reactor. So we use a CCD, and I took this picture from a book on CCDs by Jansi that everyone working on scientific CCDs usually reads. So the idea is that the CCD collects light in buckets, right? But the big advantage of a CCD, non-charged coupled device, is that the bucket that is connected to your readout electronics is this last bucket here, and you just move the charge like using potential voltages, electrical voltages. You move the charge from one bucket to the other into this serial register, then you put it on the CENNS node, which is the last stage, and that is electrically decoupled from the rest of the detector. So you can have a large detector with a small capacitance, and that's what gives you the low noise. So it's very common, right, to have people here build all the time instruments that have CCDs that operates 2 electrons and below. It's very common for CCDs because of this advantage of being charged coupled. So this is how it looks. This is what allows us to do the experiment. Because 2 electrons of noise RMS is 7.6 electron volts of energy, which is a very low threshold for a particle detector. And this is essentially easy to get. It's standard scientific instrumentation. So how does this work as a particle detector? You have a piece of silicon, your elastic scattering with a dark matter particle or a neutrino hits the nucleus of the silicon, that produces an ionization, and you measure the ionization, you move it to a pixel, and then you do the trick that I mentioned before, to move the charge around the pixel. One aspect that we take advantage of is the charge diffusion inside the pixel, or inside the silicon detector, right? So if you have a charge, if this is the pixel, we usually have pixels that are a few hundred microns. Now we are using 675 micron thick pixels. So if you put charge somewhere in the pixel, and you try to collect the charge on one side, then the charge diffuses while it is traveling, and the size of the charge cloud that you reconstruct tells you how much it has traveled. It tells you the drift of the charge in some sense. So you can measure the position along this axis in this plot by measuring the size of the diffusion. And that is nice because it allows you to reject background events that occur in the surface. An X-ray will not penetrate more than 10 microns, so it's very quickly, it's very easy to quickly reject those. And I'll show you about that in a second.
So the size depends on the temperature of the crystal, right?
The size depends on the temperature of the crystal, yes. And the voltage that you apply as well. So these are our detectors. Well, this is one version of them, but I had a nice picture, so I'm using this. So it's in this case, it's an 8 megapixel detector with 15 microns by 15 micron pixels. And as I mentioned before, it has only 2 channels connected to the readout, right? So the capacitance is very small for the readout. It's just this CENNS, so you have to move the charge all the way to these corners and then read it out. This is it's not fast readout, right? It's a very slow readout. You have to move the charge. And this is how these detectors look when you expose them to radiation in the lab. You can see muon tracks, minimum ionizing particles, right? So pretty soon, we are going to publish a result of milli-charged particles in our detector, right? Particles that have less than the charge of 1 electron, and because we have a stack of CCDs, we can reconstruct those tracks. So that's very cool. It's coming. But anyway, what I wanted to say is that you can do particle ID, right? You have muons, you have electrons, multiple scattering. And then you have these dots that are diffusion limited hits, which are the things that we expect from neutrinos and dark matter recoils, and nuclear recoils in general, neutrons also. We have done this measurement with neutrons as well. You can also reconstruct alphas. I'm not showing here, but you can easily reconstruct alpha, which is a very good thing because it allows you to control your background a little bit better. The calibration of these detectors, again, this is something very standard, right? You take 8 different X-ray sources, you put them in front of the detector, and you can see the peaks produced by the X-rays. It's very linear. You can also see, because it's a pixelated detector, sometimes you put a 5.9 kV X-ray, so this red peak here, sometimes you generate the escape lines, which means that you generate a silicon X-ray that takes part of the energy to some other place, and then you see the peak moved by the amount of energy of the silicon X-ray. So you can see that here, right? So this is an example of that. So we put 5.9 kV, and we see on the same exposure, very close to each other, the 4.2 kV from the escape line and the 1.7 from the silicon X-ray. So it's very nice to have very high position resolution because you can reconstruct these events. In a detector without this pixelization, you will see this whole thing as one thing, right? So it's very nice to see this. We measure the noise, the linearity, okay. The calibration with X-rays is good. We are going to do a calibration. We are going to use nuclear recoils So we have done, as part of our dark matter effort, calibration with neutrons. So we put a neutron source in front of the CCD, look at the spectrum that the CCD sees. We do a simulation, compare that, and understand how much energy, how much charge you produce when you have a nuclear recoil instead of an X-ray. When you have a nuclear recoil, you lose part of the energy that doesn't ionize. So that's why we have to do this calibration. It turns out that at around 2 keV, you only get 30% of the energy converted into ionization, and this drops as you go lower in energy. And we did 2 calibrations actually. So if you look at this plot, this is a better plot. So we did 2 different calibrations to understand our detectors, to understand silicon. And this gives you the ionization efficiency, right? This 30% of the part of the energy of the recoil that goes into ionization. And we learned that the model is a little bit different from what people have been, the truth is a little bit different from the model that most people have been using. We are doing more measurements on this to have better understanding, but we think that we have a pretty good idea of how this looks now. So in this experiment, we did a neutron recoil experiment. We shoot neutrons to a piece of silicon, measure the angle of the recoiling neutron, and measure the energy deposited in the silicon detector, and that way we construct the those. So we have 2 tools to calibrate, and they give us consistent results. Okay. So now we have a detector.
What was the energy of the neutrons?
About 500 keV. Yes. So when the energy is much larger than the recoil, but if you look at very small angles, then you can see
the resolution
the
result.
So, okay, I should mention, since you asked, right? We have not done a recoil experiment for the lowest threshold that our detector can see, this number. But we have done this experiment with the neutron source for that. So we did 2 of them. Yeah.
So that's actually bad news for all silicon detectors. The radar is so low.
Right. It's bad news for, it has impact on the silicon detectors that are looking. And we are working hard to try to understand if there's something, if there's any issue with those measurements. So we have a plan to do additional measurements on this silicon recoil. But now, that is now taken more or less as a standard, or the conservative standard, to put it somewhere. All right, so now you have to choose we have a detector, calibrated detector with low threshold, and now we have to choose the location of our experiment. So all this red stuff, red color, are the neutrino fluxes from the reactors. So, even though we live in Chicago, we are here in this nuclear reactor in Rio de Janeiro, and the reason is it's not because it's a nice place. It's not only because of that. It's a place where our colleagues from Brazil had set up a facility to do the experiments. So we just needed them to give us space there, and we didn't have to develop all the infrastructure of using, putting a container and all that. So we are 30 meters away from the core of a 4 gigawatt reactor, thermal, 4 gigawatt thermal reactor. So it's a very big reactor. And we are outside this white container. Okay.
Can I ask you something about the previous one? On the top slide, is that actually measured or is it a simulation?
No, it's not mesh.
It's a projection. No, it's with molding.
Because they're not all on at the same time.
Yeah.
Okay.
It's not the, yeah, it would be nice. I think people are trying to come up with tools to be able to measure these flags. Okay. Okay, so we did some estimations on the rates for the Coney experiment with the conditions I mentioned before. This plot here shows you that the number of events in event per day per kilogram per kb is very large. No? It's hundreds of events, right? At low energies, it's very large. This is compared to much smaller numbers of less than one event in these units per for a dark matter experiment, right? So, in principle, it's a little bit, it's much larger than the rates of the dark matter experiments, so it should be possible. Okay, so this is what we did. We took a lot of polyethylene and lead to Brazil, put our detector inside this copper vessel. The new detectors that we have are about 6 grams each. It's a 4K by 4K CCD with 675 micron thick. So this is very massive CCD, right? In this experiment, we have more CCD mass than LSST. So LSST is a huge camera, but these detectors are, for CCDs, these are very thick detectors, right?
So could you tell us how could you achieve such a thickness? Because you have a more pure silicon that you can deplete more?
We have very pure silicon, but also we don't have such a strong requirement on the diffusion. Now, for astronomy, people don't like this charge diffusion that I was mentioned before. So we live with that. So you wouldn't do this in an astrophysics, in an astronomy institute. It has too much diffusion. But for us it's very good because it has a lot of matter. So, okay, this is the other part. It's kind of annoying, but this is how the reactors work. The reactors are there not to produce neutrinos, but to produce electricity. So they like to be on and not off. So the reactor shuts down 1 month per year. So to change the fuel rods and do some maintenance. So typically what we have to do is measure the background when the reactor is off, and then compare that with the data when the reactor is on. Now, ideally you will want this to be 50-50, but it's 1 to 12. So our statistics is limited by the time the reactor is off, right? And I will tell you about that in a second. I'll tell you a little bit more. But okay, so we do that. And this is the first run. The first run to convince, so we had a little bit of funding from Fermilab to put this detector there, and we just took one detector, 1 gram, and put it in Rio, just to show that we could do this, right? Hoping that this would be a way to get more funding to build a real experiment. So we took 1 gram detector and were there for about 18 days with the reactor off and 15 and 18 with the reactor off and on. And then what we can do is compare the spectrum. Now the first thing I want to show you is this spectrum from 0 to 100 kV, and this is in the event rate. So the blue is without any shield, then we put some shield, the poly and lead, and we go to these red and pink curves. And what you can see are 2 main features. One is the big bump that here starts around 60 kV, those are from muon tracks, right? That cross the whole detector, so they leave a lot of charge, about 60 keV, on the CC, and then you can reconstruct the track. It's very nice. You can measure the EDX for that. That's this feature. And then, from all the radiation that you have, you produce fluorescence in the detector, and because we have very high position resolution, we can see the fluorescence peaks. You know, if you produce a silicon fluorescence when something else hits the detector, you can see both things at different events. So we can see copper peaks, aluminum, these X-ray peaks here, right? Okay, but the first goal was to show that we could do this, so we counted the rate of muons with reactor on and reactor off. And this is what I'm showing here, no? This is, I don't know if you can see the number. This is 4 to 22, no? 4 to 22. The rate of muon with the reactor off is up here and on is down there. It's important for us to show that we have a stable system, right? That the things that should not change are the same, and the results are very consistent. And then we concentrate on the fluorescence from copper. We have a lot of copper in our detector, and the radiation hits the copper, produces the X-rays from copper at 8 and almost 9 keV. So by measuring the amplitude of those copper peaks, we can see how much gamma is hitting our detector. Just to understand if there is any obvious radiation that depends on the detector. And again, we look at this, and there is no, this is the number of counts in the copper peaks, and it's consistent with no change, the number of events per day. So we have a detector that works. Okay, we completed a simple reactor on, reactor off analysis on that 1 gram and 15 days of data that was done in 2015. We saw no excess, and we were about a little bit more than a factor of 200 above the standard model prediction, which is not a surprise given the simple detector that we were using. Right? So what we did right away after that is increase the exposure very significantly, lower the noise, lower the background, and build a completely new detector with CCDs fabricated for this purpose, right? On the first attempt, we took a CCD from DCAM, packaged it a little bit different, and took it to Rio, and now we fabricated detectors for this coherent scattering search, and we did that. Okay, first I want to show you something that I consider cool images, which is, this is an exposure, 6-hour exposure of our detector. It's about half of the CCD, right? So it's in real life, this is 6 centimeters and 3 centimeters. The CCD is actually 6 by 6 centimeters. And this is how much radiation we get, so it's not a low background expected. One picture, 6 hours. 6 hours exposure. Right? And, well, you can see all sorts of cool stuff, right? Vertices, events that show higher ionization levels. But I want to show you, so this is one of the events I will show. A little shower there. So we have a stack, right? A stack of CCDs, and we develop a very nice shower that, all our software crashed, right? All went crazy. It took us a while to understand what was going on. But anyway, it's a cool detector because you can do tracking. Now you have like a bunch of CCDs like that, and you can do tracking. That's why we are using this now to search for newly charged particles. Now charged particles that will be like MIPS, but with much lower energy interaction and produce tracks on the detector. So we
How-
have a little tracker with low energy threshold.
How many do you have in the stack?
We have 12.
So what is the shell?
So this is a, we can point to the shower, to the origin of the shower, right? By doing some reconstruction in the geometry of our detector and see where it comes from. So it seems like something of high energy hit a piece of copper in our experiment and produce this shower that we can sample very well. So it's cool. It's cool to be able to see those. Okay. So let me show you how we are doing.
The image was superimposed, right? You took the information from multiple layers and superimposed.
No, this is
Just one CCD.
one CCD.
And the other
This is the
sensor.
other CCD. This is the other CCD.
And do you have any visual of how all the different layer information are combined?
We didn't make any picture. Right?
It's just all white.
We didn't make a picture, but yeah, we can have a 3D track, right? And all these guys, we are not using that, but all these, most of these are 3D tracks, right? You could do the tracking between different CCDs, and then a lot of this radiation is actually produced in association with these tracks. This is a very extreme case, but a lot of times you have a track and produces crap around it that we are not using that yet to suppress our background, but we could.
There's no magnetic field in here,
No.
right?
Okay, so, all right, so I told you, we put a very small detector in 2015, tested it, we're happy, we upgraded to the one in 2016. I want to show you the differences. So this is, for example, a difference in the noise. I was telling you that we were at 2 electrons, while actually in 2015 we were at 2.2 electrons. We ended up going on the upgrade, we went to 2 electrons. This makes a big difference, right? This small change in the noise makes a big difference when you are looking at the tail of the Gaussian distribution, right? If you set a threshold here, then this produces a very big effect in the number of events. So 10% change in the noise is a big deal.
What did you do to change the noise?
So the problem that we were having is the design of our readout cables. So we changed the position of the amplifiers and things like that. So all passive design of analog electron. All right. So this is a big deal. The other part is the dark current improved. Okay. And this is the comparison of reactor on and reactor off data in 2016. There is no difference, right? We don't. So we even in 2016 we didn't see any difference. But I want to show you compared to what we had in 2015. So the background also dropped a lot. So we did a reselection of the materials and reorganized our shield, and the background drops very significantly, like a factor of 10. This dotted line for the 2016 data here on top has to be compared with this dotted line for the 2015 data. Okay? So I'm trying to convince you that we are doing much better than what we originally had. And then we also did the same tricks of comparing muons, comparing peaks from the copper. This is the reactor on and reactor off data, copper peaks and silicon peaks, and again, things look very reasonable as no change in value. So where we are with the result, okay, one more thing before I go to the results. So we want to simulate, to have a simulation to estimate the efficiency of our detector. So we took images with the reactor off, the blue histogram here, added diffusion limited heats, right? And we use this simulation, added to real images. So all the occupancy effects, all the real noise is there, and we reconstructed those and to estimate the efficiency of our reconstructing tools. And I'll show you that in a second. Okay? But this is the tool that is the simulation that we use. Now we are doing this simulation for every single run to have a control of our, for every single operating day, right? To have a control of the efficiency for us to reconstruct these events on every day. Okay, I'll skip this because I'm running out of time. But, okay, we did a comparison. First, I'll show you the high energy comparison, no? Starting with more than 200 EVs, 200 EVs, 0.2 kVs. The comparison reactor on and reactor off is a lot more data than before. And this is from the 2016 data, right? So every year we have one shutdown. So that's why we have data from 2015, data from 2016, because every complete data level. Okay, and you can see here the reconstruction of the silicon X-ray peak. Didn't change, reactor on and reactor off. So all the sanity checks of the high energy, we don't see anything weird. You didn't expect not to see anything at 1 kV, right? And we did those checks and they look fine. So this is just to give you, before I show you what we are doing now, to give you an idea on what, how we are doing with respect to the 2015 run, no? A year before when we had only one detector. So this is the uncertainty that we have in the comparison reactor on, reactor off in the 2015 data, and this is where we are now. We have a lot more statistics, lower error, and things are progressing well. In this case, you know, the standard model is 0.04 in this case, so it's still very low. I'll skip this. So we, well, I cannot skip it. We have to do a diffusion model of our detector. So for each muon that we get in our CCDs, you know, this is a muon on the CCD, we perform a measurement of the diffusion of the muon. So you can see that this muon crosses the CCD, but this side is very narrow and the other is thick. So you can measure how much the charge is spreading inside the silicon. So we have a diffusion model that tells us how big is going to be a hit depending where it happens in the silicon. So that way we can suppress the X-rays that happen on the edge and drop our background. It's like a self-shielding detector. And the thicker you make it, the better it works. So this is important. We also do, for each event, this is an example of an event, no, where you can see the pixels and the number of electrons in each pixel. We calculate the likelihood that that event comes from fluctuation on the noise. Right? Because we are looking at the very low energy star, so we can calculate how likely it is that that event is just a fluctuation on the Gaussian distribution of the noise. So we calculate this likelihood, and we put a cut on that likelihood. So, okay, this is a, so we calculate this likelihood, and you can see here this goes from 0 to minus 100. This is the likelihood. So for fake events, you can see this rate distribution, right? And then you can see for noise, for neutrino simulated events, you can see this distribution here that goes all the way to minus 100. For noise events, you can see this red distribution. So we put a cut so that you don't really expect any noise fluctuation to go into that, to pass that cut, and that allows you to purify your sample, suppressing low energy noise, and then this is the kind of efficiency that we are getting. So I was showing you before data that started around 250 EV, So what I'm telling you now is that with these additional tools for selecting events, we go much lower in energy, right? That's where all the nice data for the coherent scattering is. No? And this is the work that we are doing right at this moment. No? Okay, I cannot yet show you the result here. The only reason is because we have it's easy, no, to put that efficiency and calculate and do the comparison, but we are worried that we have not done all the systematic studies we understand well the statistic, but we have not done all the systematic studies that are especially important at low energy, right? But I want to say the following. The standard model rate in this scale is 40 DRU at 200 dB, and as you will see in a second, when you go below 200, it goes up very fast because the event peak. So it goes up by a factor of 10 if we can get to the energy on this efficiency plot. No, the energy is here.
Why is your efficiency so low? Because your baseline resolution is very good, but what is you're driven
by this cut?
By
This
this
likelihood
cut is really-
cut. Yeah. So they trying to make sure that this doesn't look like a fluctuation on the noise.
But your baseline resolution, I mean your noise baseline looks pretty good.
Yes.
So the question is, it looks like your threshold is like 100 times sigma. Like
Yeah. So for 1 pixel, if you're looking at 1 pixel, then the noise is 7.6 dBs, right? If you're looking at a single pixel. So you have to be about 5 sigma, right, from that. So that takes you to 30. So if you have 1 pixel at 5 sigmas out of hundreds of samples, with each sample 16 million pixels, is still likely to be noise. Right? So that's what this is showing us. The distribution, because you sample the noise a lot of times. So the distribution of events from noise there is very large. Maybe I have it.
it's okay, you can take it.
Yeah, so it's the combination of having a lot of samples and a lot of pixels. But it's true that this is with our most pure selection, this is our efficiency.
So you're being conservative on that kind.
We are being very conservative.
Right.
Very
So
conservative.
eventually you probably want to do something different,
Right.
right?
Right. We want to, yes, so eventually we want to be smarter for selecting our events. Strictly speaking, if you have a good model of the noise, you don't need to cut it like that. Right? Okay, but even like this, it's starting to get very interesting. And again, the reason I'm not showing here is because we are looking at the systematic effects before putting a number, because now we are at 700 DRU, so we are already able to put constraints on new physics. So we have to make sure that it's right. And this is how the number of events changes. Now, what I was showing you before with about 200 EV threshold was here. With the new likelihood hats, our threshold, starts somewhere there, and as it gets more interesting as you go along. Okay, the other big aspect of this is that we have improved our statistic. The first data that I showed you from 2015 had this amount of data for reactor on and reactor off, right? This is the reactor off data, reactor on data. So, and that was the mass of the detector. In 2016, we increased here with good detectors, reactor on and reactor off. And just now, we had another shutdown in February, where we are here, right? We have the full mass, 50 grams of working, very nicely working detectors. We have 12 detectors, but some are not so nice at low energies, so we don't use them for the analysis. So, we have 5 times the statistic that I was showing you before. So we are very close to the standard model, and 5 times the statistics that we were showing before. It starts getting interesting, and that's why the other part that we are improving is the analysis of the data. So right now we do the simplest thing. Take data with the reactor on, reactor off, and subtract. Is completely dominated by the 1 month when the reactor is off. The rest doesn't matter much. I mean, statistically, is dominated. The error is dominated by the limitation of the reactor off. But you can do much better, right? So we are running a full GEAN simulation of our experiment, understanding the radiation of our shield. This is a comparison of the simulation, of the GEAN for simulation and the data for the spectrum. The idea is that we want to make a model of the background and subtract the signal to the background model and not be limited by we probably still have some uncertainties of the background, but will not be limited by the statistics of one run, right? So this will improve our factor. So I'm trying to convince you that we have a lot of very interesting data that we are looking at, and we are certainly, we are close to, will be within the reach of the statistical reach for the standard model next year, 1 year from now, right? When we get the data from the next shutdown. Every shutdown we get this data, so we expect the next shutdown to be as efficient as in February 2018, and we'll see the standard model there. But we certainly now are in the reach of new physics like the one I was showing you before. So that's what our focus is now, is understanding that part. Okay, but the story doesn't end there. We have a new detector that lowers the threshold by a factor of 10. And this is what I wanted to tell you now. So this is how the CCD works. I mentioned before, the CCD, you move the charge from one pixel to the other, and then you put it in the CENNS node, right? So you move it, in this case, you move it to the left, and then down toward the CENNS node. So a new type of skipper CCD, well, it's not so new, right? In 1990, this same guy that I mentioned before, James, proposed the development of the skipper detector, in which you put the charge on the CENNS node, then you take it out, you put it again, you take it out, and you keep measuring many times without destroying it. So the noise drops to 0. Right? So you can put
You put it again.
yeah, so you put it here, then you take it back into the serial, then you put it here. No? So you measure 4,000 times and the noise drops to 0. Let's see if I got my movie to work. So this is how it works. So this is one readout. So the skipper amplifier is a little bit noisier than the standard amplifier. So in one single readout, instead of 2 electrons, you get 3.5. So this is the distribution for one readout with the skipper. This is real data, by the way. It's not a simulation, right? So I'm just taking more and more samples of the same data. It's the same exposure. There was 1 electron here, right? So I'm focusing on that electron. This is the number of samples that you take. Oops. So it's very straightforward how it works, but it's cool, right? You will see that at the end you can select this single electron event there that is completely washed out at the beginning, and you don't lose anything. Well, you
What
lose
frequency
time.
you do? Back and forth?
Huh?
At what
4,000 times. So this is the number of times.
Sure, but that's the total number, but at what frequency?
Oh, at what frequency? Let's see if I have that. So we take like 4 microseconds per sample. Okay. So So this detector was designed in 1990, but it never actually got it to work. And we worked with Berkeley for many years. And Javier Tiefenberg, who's a scientist from Fermilab working in my group, demonstrated this in 2017, so last year. I mean, really, we had a lot of people looking at it. You have to put the right voltages exactly right. At the end it works. Now we understand how to make it with. But it's very nice. And this is how it counts electrons, right? 0, 1, 2, very, very impressive. Let me show you a couple more. Okay. Just to mention, no, it has a big impact on the number of events as you go lower.
These are currently much lower mass also, is that true?
Much lower mass, yes. So these are 1 gram each. And we just completed a contract to fabricate an experiment with 100 grams of skipper.
It is possible to escalate.
It's possible to escalate.
Is it
But
LBNL that does it?
the fabrication, the design is done at LBNL. The fabrication is done somewhere else.
Oh,
By a company that fabricates CCDs. Also. I like this plot also. Well, I like a lot of the plots for the skipper, right? But this is a nice one because it shows you this is all the way to 50 electrons. Right? We put a little bit of light, and you can count. This is also nice. No, this is show the line for 5.9 kV. No, so now I will concentrate on this red region. And you can see all the peaks of 5.9. Okay, so you can measure final factor, absolute gain of the thing, perfect, right?
the electron counter.
Yeah, it's an electron counter all the way to all right, so what are we doing with this? The main thing we are doing, and this is a different topic, but Rupak asked me to mention it, is the CENNS experiment. So we are looking for very low mass dark matter. The best way to look is electron recoil, not nuclear recoil anymore, because the mass is so low that it's hard to produce ionization of nuclear recoil, but you can hit an electron that has a smaller gap so you can see that. And okay, so we are looking at low mass dark matter by looking at electron recoils. This is a topic that is, in fashion now, dark sector, dark photons. And this is one of the plots that shows the mass of this dark matter and the cross-section with electrons. And you can see the current limits from xenon 100 and xenon 10 for single electron observations, and what we can do with CENNS with 10.3 hours of running. So this is CENNS 1, so it's 1 gram doing 10 hours. This is CENNS 10 grams for 1 month. Anyway, so 100 grams is very powerful. And this is because the number of electrons that you expect to produce in silicon due to ionization for a dark matter particle with 10 MeV in this case, right? So it's a cool tool to look for this. And we are doing this experiment. We installed a prototype that is actually less than 1 gram now in the Venus panel. Again, this is a prototype that was built parasitically with other CCD production, so it's not the best detector for this, but we established this very close to where your colleagues will put Nexus, right? Well, we are running, right? And a few weeks ago, maybe a couple of months ago, there was this result from the EDGES experiment about very low mass dark matter, and we decided to use our data from the lab, not even underground, from the lab that we took when we were testing the detector. So 0.019 gram days of exposure. I feel ashamed of the little one. But you know, for a few hours of the best detector that we have, we run in the lab before taking it underground. And this is a spectrum of 0. We are not even pushing for the minimum node, so we're doing 800 samples. So 1, 2, 3 electrons, right? And then with this, we could already, with this detector, no, a less than a gram detector running for a few hours in the surface without any shielding, we were able to put already constraints on electron recoil dark matter that are scanning a new region, no, on this range below up to 5 mF, no, below 5. So it's a very nice demonstration of the powerful of a new detector, right? A new detector, you run it, and I know that you know, super CDMS is going to put something in this area very soon. Well, I'll skip this. Right. So, maybe just say something. So the point is that this edges experiment looking at 21 centimeter proposes light mediator dark matter that was like 1% of the critical density, and that's what with very low masses. And Sensei, the reason why we did this test with the data in the lab is that we could reach that experiment. So we started constraining that section. As I have to say, super CDMS will have the same thing. Okay, so CONI is poised to produce very interesting results of the detection of CENNS in reactor neutrinos. As I say, we are extremely close to the standard model. We are certainly within reach of the new physics from the statistical point of view, and we are doing the systematic analysis now. And we are looking forward to start joining Coherent in measuring Neutrino-Recoils. We have very exciting prospect for using the new Skipper CCD that I showed you before. We have some R&D going on now to build a 10 kilogram detector with this technology. It has, as I say, many potential applications in stereo neutrino experiments with very short baseline or reactor monitoring. And maybe we can test that at the reactor that you have here. That's why a real reason for my visit. Okay, and we are already using the Skipper CCD for dark matter science. I had to show you very quickly, but we had the first results a few weeks ago with the data that I'm experimentally, I'm a little bit ashamed of running the detector for so little on the surface, but it produces a new result.
So what kind of refrigeration, if any, do the CCDs require?
The CCDs work at 140 Kelvin, so we just pulse tube refrigerator.
How do you want to be temperature? Is it just mass reducing the same?
No,
So
what we are doing now doesn't scale, right? I mean, let me show you. So what we are doing is, this is 5.6 gram, it doesn't scale. So
is it 1 meter?
675 microns. 675. So what we want to do is build. So this is the sensitive part. So I work at a lab sided where my colleague Ricardo built large detectors with a lot of little pieces of silicon. Right? We know how to do it. You just have to put the electronics, cold electronics right next to this, the digitizer right there, bring all the signals out with a hybrid cable, and then it becomes more like a CMS detector, right? So that's the plan. So that's the funding that we have now is to start building detectors in that way, using the hybridization technology from high energy physics, not looking like a hack of astronomy capital, which is this is like a in between the two.
Is that the Department of Defense funding? If you who funded that?
So yes, in part. Well, they talk to the lab, and yeah. So that's the idea. So we don't have the money to build the country, right? We have the money to demonstrate that we can build a 100-gram experiment with the technology that will allow us to scale it to 10 kilograms. And also this is independent of the sensei activity. The sensei activity is 100 gram, is a much shorter time scale, and we will build that by brute force, scaling this just the way we know how to do it.
It's more like reactor monitoring potential.
Yeah.
On the skipper technology, have you guys, at some point, I would imagine, going back and forth, right? You statistically reduce the noise, but I would imagine you start losing charge at some point. Do you have any feeling of what that number is?
So the charge transfer inefficiency on the CCD is something that we measure very well, right? For when you get to close to 100,000 electrons, which is to fill the pixel with charge, then the charge transfer inefficiency can be 10 to the minus 5, 10 to the minus 6.
Okay.
Right? But when you have one electron, it's much larger than that. So we have some...
Much larger or much smaller?
Much smaller.
Okay.
The inefficiency is much smaller. So we don't see any degradation. And I have some...
So technically you can go to 1 million in the sampling and you will still be fine, right?
Yeah,
you
are starting to see dark current. That's the limit.
Okay.
Okay? So the limit is the dark current. But if you look at this, for example, I will claim that this so we do this, right? This shows the noise as a function of sample, right? How it goes. So this shows that there is up to, a few thousand samples, there is really no deviation from a Gaussian in the noise. That's one thing. And the other is, when you look at something like this, right? This is with 4,000 samples. You can calculate exactly what the gain is, because you can see these guys. So you will start seeing the things move. And we haven't seen that yet, but it should happen at a very low level. If we had a lot more light, then you will be losing 1 part in a million, every time you move it.
At microsecond time scale. At microsecond time scale.
At microsecond time scale, yes.
So my question is, so how does it work? Each time you pick some input to your sense node, let's say, then it goes back and forth. So it takes, let's say, 1,000. So it takes 4 milliseconds per pixel to react.
Yeah, these detectors are always reading out. I mean, we just read out the detector 1 pixel after the other. The active part is still taking data, so it doesn't matter. So you don't have dead time, but you really lose any timing.
No, you don't have pile-up issues and so on.
No.
It's so clean.
Yeah. So, yeah, it's I mean, even this, to give you an idea, even this thing here, which is 6 hours, this is a 6-hour exposure, has a per pixel occupancy below 3%. So there is very little variation once you look at all the pixels.
And these are low background. Any other questions? Thank you.